Start with this. Okay. So thank you. It's always a pleasure actually to come back to Presidency College. So 3 years spent here were some of the most memorable times. Getting into ISC was very good after doing BSc at Presidency College. But the worst part was actually leaving Presidency College at that time. It had become such an important part of our life. Lectures, PLT1, PLT, then a lot of times spent in the boys' common room. I don't know if the tank is still there. We used to have the tank, the badminton court near the Kolkata. Everything was actually quite so it's always a very good feeling to come back to this. And this is actually the first time that I've come back to college where I'm actually on this side. That's this lecture. Yeah. So this is the first time that I'm coming back to give a lecture at this college. I hope that in future also. So today I'm going to talk about my research, which I have been doing for the past few years. So since about 2016 or about 2017, I've been involved in the research on topological behaviors. So since I prepared this talk for students, it will not be too technical. I will try to give you a feeling of what these materials are. And rather than, of course, a lot of things can be derived here. You can write down equations and solve topological states. But I'm an experimentalist, so I would like to give you a feeling such that you can visualize what these topological behaviors are. And what are their exotic properties? And why are they so amazing? And the prototype behavior that I've been working with is multi-level attention. Why multi-level attention will also come. As the outcomes. So, who here is familiar with the concept of topological display? First of all, how many of you know this person? Raise hands, you know. Okay, very few. I expected more. So, who is this?
Sheldon Cooper.
Sheldon Cooper. So, in season 4, episode 14, he actually puts up a slide, and the question he asks is who here is familiar with the concept of topological display? So, answers. Who here is familiar with the concept of topology? So you have heard the word topology, many people must have heard it. You heard it in the context of mathematics or theoretical physical context. But over the past 2 decades, this has become a very, very active area of research, not just for theorists, but experimental physicists, material scientists as well. So there has been a lot of effort which is directed towards this research of topological behaviors. Now, if you see here, there's a material which is drawn here, a schematic is drawn. And if you see the schematic, what is written here is invisible HgTe. They also actually use this material, cadmium telluride, mercury telluride, and cadmium telluride. Sandwich of mercury telluride in between cadmium telluride. The reason why was at that time, in 2007, first paper which came on two-dimensional topological insulators, I'm adding the word two-dimensional, was on this particular material of gradient. So, in short, first I will give a very try to give you just a one slide introduction. What is a topological system? And then we'll take a slide deep to understand some concepts so that it's easier to appreciate what topology is. So, I have provided just two types on two-dimensional topological insulators and three-dimensional topological insulators. It's just so that so, all of you know what a two-dimensional system is, or what a three-dimensional system is, or a 1D system. Everyone knows what is a 2D system. When electrons are confined to only two directions, when you actually spin the material down and down, so that the movement in the z direction is not now. Electrons can only x way. So that is actually a two-dimensional system. And a 3D is everything. In reality, everything is just. So topological insulator is actually a material where the bulk of electrons is a material such that the bulk of this material is actually insulated. So if this is a 3D system, so the bulk, the inside of this material is completely insulated, but the surface is conducting. So only the surfaces are conducting, but the bulk of this material is insulated. So if you apply a voltage across this material, so for an insulator, if you apply a voltage, there will be no current. For a metal, when you apply a voltage, there will be some current. For a topological insulator, of course, there are conducting states. So if you apply a voltage, the current will actually flow only along the surface of the material, and it will not flow through the bulk. So pretty amazing. You have this material, but only the surfaces are conducting, but the bulk is completely insulated. Okay? So this is for a three-dimensional system. Now for a two-dimensional system, if I thin this down enough, you have a two-dimensional system. Once again, the same concept applies. The bulk is insulated, the surface is conducting. But for a two-dimensional system, the bulk is actually the surface. And the surface is actually just an edge. So the surface of a two-dimensional topological insulator is completely insulated. So if I apply a voltage, the current will flow only along the edge of it. Okay? Now this is one property, that the current only flows along the edge. Other property is that the spin of the charge carrier, the spin of the electron is locked to the momentum. This phenomenon is called as spin momentum lock. So, if I have a spin up electron, it can move only in one particular direction. Because the moment I reverse the momentum, the spin will also reverse because the spin is locked to the momentum, and this holds for. So if you see that, so if you see, for example, over here, if you have an electron of up spin, it can propagate, let's say, in clockwise direction. The moment I change the spin to down, it will propagate clock, maybe counterclockwise. Same for the surface. You see, the spin is always locked to the momentum. Now, this has some very unique implications. The spin is locked to the momentum, then it means that you are scattering. Not all types of scatterings are allowed. Okay, and if not all types of scattering is allowed, that means that in certain conditions you can reach what we call as the spatial test transport, because they're asking that scattering is surface. So this is a one-line introduction. Now, how all these things were discovered, that is something what we will focus on. But in order to focus on, we will focus on. In order to explain this, we will actually try to understand. So I will concentrate mostly on individual logical experiments, which we are all focus on. And this material, this is state where the bulk of a 2D system is insulated and current flows along the edges in a way that the spin up electron moves in clockwise direction and a spin down electron moves in a counterclockwise direction. This state is known as a quantum spin on state. Okay, we call it counterpropagating edge channels, which means that there are two edge channels over here in this state. The spin up electrons moving in a clockwise direction, spin down electrons moving in a counterclockwise direction. And we are going to see how we can realize this state in the lab, how we can actually measure this state in the lab. Alright? So, have any one of you heard quantum spin Hall state? Yes, no? Okay, no problem. Let's simplify. Let's remove the word spin. Has anyone heard of quantum Hall state? No. Okay, let's simplify further. Let's remove quantum. Has anyone heard of spin Hall? No. Okay, let's simplify it even further. Let's remove the word quantum spin. Then you are left with Hall effect. How many of you have heard Hall effect? Come on, everyone should raise the hands, right? Don't be shy, okay? And interrupt me anytime you have a question. Alright, that is what we are going to do. Let's start from something which you know, okay? And that is the Hall. So, I'll explain quantum spin Hall, but before that I will go quantum Hall effect and then we'll come back. Alright, let's consider a simple picture of the atomic
These calls was today's.
Okay? So if you have atomic insulator, we have sp orbitals, which you know, and you have this kind of energy gap. Sorry about this bad format. So we have energy levels which are separated by a gap. In quantum Hall effect, that's something very similar to this. So it's not very different from what you already know. Something very similar happens, but it happens when you have a two-dimensional electron system in a perpendicular magnetic field. Now, if you apply a magnetic field, what do charge carriers do? If your electrons are moving, let's say, in a two-dimensional plane, and you apply a magnetic field perpendicular to it, what happens? Lorentz force and louder.
Actually, particularly for the cyclotron.
Absolutely. Electrons move in a circle, right? This is what we know. So this is what happens. Electrons actually move in a circle. And if we actually try to solve for this quantum mechanically, then we will see something similar. That we have energy levels which are separated by a gap. And in order to understand how this happens, how this gap occurs, we have to solve the Raychaudhuri. Okay? So now let's start with what I promised. Classical polynomial. This is something which all of us want. So what do we have? We have a system over here. We pass current along the x direction and we apply magnetic field along the z. Then what happens? Lorentz force is there. Electrons move in a direction which is perpendicular to both the current or the electric field which you have applied and the magnetic field. So in this case, the electric field is along z direction. Sorry, x direction. Magnetic field is along z direction. So my electrons actually move along the y direction. And because the electrons move along the y direction, then it develops an electric field which sort of suppresses the movement of electrons along the y direction. So we develop a voltage which we call as topology. Correct? And the voltage which is developed is related to the magnetic field of keep increasing the magnetic field, the voltage increases. And what we can do is we solve this for the resistivity components in the presence of a magnetic field. How will the different components of resistivity evolve? Alright? So when we don't apply a magnetic field, we only can talk about resistance or resistivity, which is rho. But the moment you apply a magnetic field, we all know that resistivity is not just a number, right? It's a tensor. So you have different components of resistivity, the longitudinal component which is rho xx and the transverse component which is rho xy. So rho xx longitudinal component is measured along the direction of the current and the transverse component is measured along the direction perpendicular to the current. This is something which we all know. Then you solve for Ohm's law, you use the equations, you kind of know what the magnetic force, what the force of the electron is q v cross v. You equate it to the force which is required for circular motion, which is mv squared by r. From then you get certain relations for the velocity of the electron and the electric field developed in the y direction. And after that, this is just algebra. So I'm not going to go through it in detail. It's a simple algebra, you will do it. And what you will see is that the longitudinal component of resistivity is actually independent of the magnetic field. So the longitudinal component of resistivity is 1 upon n mu. But the transverse component increases linearly with magnetic field. It depends on the magnetic field and the density of the sample. Where n is the carrier density, which could be number of electrons or the number of holes. Okay? So this is something which we call resistivity, which increases as a function of magnetic field, and the longitudinal resistivity which remains constant. And this is rho xx. If I write sigma xx, which is longitudinal conductivity, then that will be n e mu. What is that? Sigma is equal to n e mu. Which model gives it sigma is equal to n e mu? Exactly. So the Drude model, conductivity in Drude model, sigma is equal to n e mu, and the longitudinal resistivity actually is not affected. It remains same as what you would have got. Sigma is equal to n e mu. You see that is exactly the same order. So what do I expect when I apply a magnetic field for a 2D system? My longitudinal resistivity will remain constant, my transverse resistivity will increase. This is what these equations give us. But we should be able to do it, measure this theory. So here, what you see here is an actual sample over here. And okay, the picture is not so nice, but there are wires, tiny wires coming out of these samples. So there is one wire connected here, one wire connected here. This is used to couple a fast connection to the sample. And then there are two wires over here which measures the longitudinal voltage, and one on the other side of the sample which measures the transverse. So that we can how the wires is visible. Is it visible? Alright. So we pass current through these wires and we measure the longitudinal transverse voltages. So this is for a sample which is big enough so that we can make these attached wires. Often we deal with materials where we cannot make such big samples, where we need to actually make the small samples to study these. Because it's not just for measuring the output, or we can measure the samples, but we have various other. So for which we actually need to fabricate samples which are very small. In which case we use techniques called as lithography. It can be optical lithography, in which we use light beam to make pattern, or it can be electron beam lithography, where we use beams of the electron to make patterns that design. So how many of you know about, how many of you have an idea about lithography? Later towards the slides, maybe I can say a few sentences. So here also we can pass current along with direct measurable longitudinal and now, if I actually, this is the actual experimental data. So if you see the red one, it represents the transverse resistance. So if you see at B is equal to 0, it is 0, and as magnetic field increases, this increases the and the longitudinal resistance, the equation predicted that it will be constant. It's not actually constant, but it's weakly dependent on magnetic field. If you see, there are certain ripples which start flowing. But the longitudinal resistivity has this ripples, but the transverse resistivity actually increases the as we saw. Okay. Now this is only the one test. And this is where the classical law effect actually is changing. Now what happens when you start to increase the field? What you will see that your longitudinal resistance does not remain constant anymore. These ripples which were tiny till 1 Tesla start to increase. If you see now the ripples are actually larger than magnitude. You increase the field further, you start seeing oscillations in your longitudinal resistance, and your transverse resistance, which was supposed to increase linearly with magnetic field, it starts showing plateaus. Plateaus meaning that you see over here for a certain range of magnetic field, it is constant. Increases again, constant. Increases. Okay. This is still 5 Tesla for someone to examine. And this is and one important thing here. We have not discussed what material system is. We just said that it's a two-dimensional system in a magnetic field. That means that whatever the material is, it does. Any two-dimensional system of sufficiently good quality. This is the thing. Sufficiently good quality. How do we know the quality? By measuring the quantity known as mobility. Sigma is equal to n degree to that mobility. So, a sample or a material system which has good mobility, if you make it in 2 dimensions, you put it in a perpendicular magnetic field, and this is what it is. And if you see at higher magnetic field, your longitudinal resistivity actually touches 0 almost. And another important point is wherever you have this minimum in the longitudinal resistivity, you see a better in our example in transverse. To elaborate this further, this is a sample which is of even higher quality and even lower temperature. Very important, temperature also has. There are some materials which can show this kind of effect at room temperature. In general, the temperature is very low because we want the thermal energy to be very, very small. So when I say low temperature, typically these behaviors can be observed for temperatures below 4. Okay? 4 Kelvin, 4.2 Kelvin is the boiling point of. So below 4.2 Kelvin milligrams for various material systems. So this is for a material system which is of sufficient heat, which is given better volume. Here also we see that for low magnetic field, still almost a Tesla or lower Tesla, your longitudinal transverse resistance increases linearly. Then you start seeing these plateaus and perfectly flat. And whenever you have a plateau, you see a minimum in the longitudinal resistivity, RMSX. Rxy shows plateaus, Rxx shows positive ends. And the minimum actually touches 0. When I say touches 0, it doesn't mean it is close to 0. It is equal to 0. Okay? Any questions? So this is the experimental observation part. Let's suppose that this is what is observed in experiments. Now one question which occurs in the mind, okay, these are plateaus, what are the values of these plateaus? Turns out these are not random values. These are values which depends only on fundamental constants. And that fundamental constant is h over e squared, where h is the Planck's constant and e is the electronic charge. All of you have course of quantum mechanics? Anyone who didn't have a course of quantum mechanics till now? First year? Second year? Okay. What do you know about Planck's constant? H or E. So this is h is the Planck's constant and e is the electronic charge. And h over e squared is the value which we now, which is known as Klitzing constant in the name of Sir Professor von Klitzing, who actually observed this effect for the first time. Okay, so this is known as Klitzing constant. It's also known as the quantum of resistance. So one quantum of resistance, like you have. So this is the quantum of resistance. This has a value of 25.812 kilograms. Turns out that these plateaus are exactly 1 over an integer multiplied by this number. So when it is written I is equal to 2 here, this means this plateau is exactly Rk divided by 2. We have Rk by 3, Rk by 4, 5, 6, 7 is missing, then 8, 10, 12, that's how it is. So if you see that we actually first see the even plateaus, then the odd plateaus also start. And that is something which I will give you the answer because of the splitting. Okay, when the Z1 is splitting is high enough at high magnitude, only then you have a question.
Why is 7 to 9 always values?
That's what I said. Because the up and down distance are degenerate, they occupy the same direction. Okay, so you have to, when you apply magnetic field, you have the Z1 splitting. What is the value of the Z1 splitting? G mu B into magnetic field. So depending on the temperature, if this splitting is larger than K2, then you will see those plateaus. So at low values of magnetic field, this splitting doesn't get larger. But the moment you come to this magnetic field, you can see that okay, there is some splitting which you can absorb. But now for 3, Rk by 3, this splitting is larger so that you can absorb it. So that's a short. Okay? So this was observed by Professor von Klitzing, for which he received the Nobel Prize in 19.
Why it is truncated at I equal to 2? I mean, if I increase magnetic field more,
It will go to 1. Then like you see here, it was 3, then it increased, it came to 2. If I increase it further, it will remain as 3, then it will increase and go to 1.
I mean, I am saying that if I increase the magnetic field more, then what will happen? It will remain constant.
Okay. So it depends on material system. So right now what we are talking about, you see here, it's not just one object that added the word to it. Okay? So we are concentrating on what we call as the integer concept. If your material is of very nice quality, then what will happen is that the moment if we keep increasing the magnetic field, we will also start seeing some fractional. Clear? Okay, so but that is not the focus of this talk. We won't go into that. Okay, it's a bit more complicated. So we will focus only on integer quantum conflict where we observe the values only one. Okay. So now our objective is to find out why these values are. And how can we sort of explain the fact that my resistance remains constant for this magnetic field, and that constant is exactly some ratio of h over e squared. Now, very important. When I say that Rk, this value is Rk by 2, once again, I don't mean that it is close to Rk. It is exactly equal to Rk. And when I say exactly equal, so now the quantum Hall effect, we call it quantized plateaus. Why? Because it is quantized in units of something. So when we say it is quantized plateau, it is quantized in units of h over e squared. Now, the quantization is so perfect, so perfect, that the standard of resistance now is in terms of this particular effect. The resistance standard is defined as the value of this field, which people have measured with great accuracy up till this number of decimal place. So this number is not just written like this is actually been measured experimentally up to this many decimal places. Okay? It's clear? So nothing is approximate. The value should be exactly equal to the plate space. Questions? Okay. So now our objective is to try to explain this. Before that, a bit of a so this actually is 5th of February 1980 at 2 a.m. Professor Monplitzig, he was actually measuring it. This was measured in 1980, so it's not that you can immediately plot it in your laptop so fast. So you see how it was plotted here in graph paper. And there we saw that, okay, my Hall resistance doesn't change, it's quantized, and these have his notes from his notebook. And back then, by doing some calculations, we were able to see how certain values of magnetic field, my resistance of Hall voltage is quantized. This is actually 1.6 volt. Alright. Now, what we will do? How to explain this quantization? So, okay, not all of you have had a course on quantum mechanics. So, first we will take a semi-classical. Okay, so in the semi-classical approach, we will try to see what happens to a 2D system in a magnetic field. So, as you already said, that if you have a two-dimensional system and I apply a magnetic field, then my electrons will undergo a cycle from within. These electrons will move in orbits. And mv squared by r is equal to evb. Everyone understands this figure. Okay. Now, what do? We say that, okay, not all the orbits are. We try to invoke the notion that electrons are not just particles. Semi-classical approach, which means that we will say that electrons also have a wave character. So that means if I say that electrons have a wave character, there is a de Broglie wavelength which is associated. What is the value of that de Broglie wavelength? E by lambda. Very good. Now we say that, okay, not all orbits are allowed. Only those orbits are allowed when the electron wave is on itself. So this is an allowed orbit. So this is not allowed. Okay? Clear? So now when I impose this condition, which means that the circumference of the orbit, which is 2 pi r, must be equal to n into h by n. Is it clear? 2 pi r is equal to n into h by n. Okay? And I can also get what resistance is, what the radius is in terms of magnetic field using this. Alright. So now if I choose all these equations, I can get a relation for the momentum. Okay? So now if you see over here, we have the automatically, so it can impose 1 wave, 2, 3, 4, that is why an integral number of wavelengths has been allowed. So there is this integer function. So this gives me momentum, allowed values of momentum. Now since we have talked about only allowed orbit, so the allowed values of momentum En square is equal to n h cross of E. Converts it into energy E squared by 2n. So n h cross EB by 2m, which is equal to half into n into h cross into omega c, where omega c is equal to E into B by n, which is the cyclical. What we call as the cycle. Omega c is equal to EB by m, where omega is the cycle. Now you see that not all energy levels or not all values of energy are allowed. There are only certain allowed levels, and your n is an integer. So if n is equal to 1 and n is equal to 2, and then you subtract it, what will you get? What will be the separation between the two energy levels? Absolutely. So what it says that the difference only allowed, so allowed energy levels are separated by a magnetic h cross c, where omega c depends on the magnetic field. So you can actually change the gap between the allowed molecules by changing the value. Okay, this is the semi-class. Clear? Any questions? Okay. So only the second years didn't have a course on quantum mechanics. Rest of you have a course on quantum mechanics. Yes? Yes, so your second year. Schrödinger's equation, how many of you have to solve? Second year. Okay. All. But we have heard of Schrödinger's equation. All. So now what we are going to do, we are going to do a full quantum mechanical calculation. Now in the full quantum mechanical calculation, what we do, we solve this particular equation.
Now gets
H. So if my wave function is x comma y, so remember we are talking about two-dimensional electrons in a magnetic field. So if we have two-dimensional electrons, so I take my wave function to be a function of x and y. And the Schrödinger's equation which I have to solve is H psi is equal to E psi. Alright? Now I have to solve this equation in presence of a perpendicular magnetic field. And how I incorporate my magnetic field into the equation? I introduce a vector potential. So the vector potential which I introduce is A, which is equal to 0 and x into B. B is equal to curl of A. All of you know electromagnetic discourse. Now, if you take this value of A, which is 0 and x is B, and if you take a curl of this, you will find that we have a magnetic field B, but it is in the Z direction. Okay, this is what our problem is, solving the Schrödinger's equation in a perpendicular magnetic field, and we do it for this particular choice of vector potential. And this gauge is known as lambda gauge. Clear? Now, of course, some of you can say that, okay, all I need is a magnetic field in the Z direction. I don't need to use this particular value of vector potential. I can choose some other value of vector potential in which the y component is actually 0 and x component is some y negative field. So that, if you take a curl of that, with the negative sign, if you take a curl of that, you will also get a magnetic field in the Z direction. Or you can choose a mix, where you have some component in x and some component in y, and you take a curl of that, and you still get a magnetic field in Z direction. So there are various values of the vector potential which will give you a magnetic field in Z direction, none of which is actually going to change the resistance. Whether you solve it in this particular gauge or through some other gauge, your answer will ultimate physics remains. Okay? Now, how is my magnetic field incorporated into the Hamiltonian? Yeah, Hamiltonian, what happens is that this is also something you might have done in your electrodynamics course. So if you have a vector potential A, then your momentum P transforms to P minus EA. All of you know this? At least some of you know this, right? Okay, great. So your momentum changes from P to P minus A. So this is what my Hamiltonian becomes. Hamiltonian is simply P squared by 2m, but your momentum is P minus EA whole squared by 2m. Now we are working in two dimensions. Now when we are working in two dimensions, I am going to separate the x and y components. We use what we call as the separation of variables. In the separation of variables, I don't have any x component in my vector potential, so I get 3x. And for y, it is called 3y minus e into dx. And this becomes whole square. For e is b, because my vector potential is the y component of vector potential is x into b. So I get p minus e into dx whole square. Now this we are going to solve by separation of variables. I assume now if you see here, for y, for py, it's just py squared. There is no y coordinate which appears on this. For x, the x coordinate appears. But for y, it doesn't appear. Which means that I can take the solution for the y component into plane. Alright? So if you have a free particle, let's say, if you solve a one-dimensional problem, px squared by 2, Hamiltonian is px squared by 2. And you want to solve for the energy fields, you assume a trial solution e to the power I into k into y, which is px e to the power I kx. So you assume what you get is plane wave solutions. So this is exactly what we are doing here. We have plane waves in the y direction. So we break down my wave function psi of n, phi of n into e to the power I into k into y. And when we rewrite the Hamiltonian to solve for this phi. So now what happens? I replace the momentum operator Py with momentum operator eigenvalue, which is h cross k. How many of you know quantum mechanics people already know the eigenvalues of momentum is h cross into k. Okay? So I simply now reduce my Hamiltonian where I write down the eigenvalues for the operator. So now my Hamiltonian modified Hamiltonian x prime is 1 by 2m px square plus h cross ky minus e into v into x. Okay? Great. Now we are going to just do some sort of rearrangement. I assume that xk is equal to ky into lv square, where lv is h cross by ev. Just rearrange, nothing else. And ev by mc, ev by m, I write it as omega c, so that my Hamiltonian becomes px square by 2m plus m by 2 omega c square x minus xk square. These two are identical equations, just rearrange, and I use some symbols. Instead, I use xk to be ky equal to e square and omega c is equal to e by m. Okay? Just algebra from here to here. Nothing else. How many of you realize what this is? Louder. Exactly. So what do you have? This is actually a shifted harmonic system. Because you have omega c square x minus xk. That means it is done. Now you no longer need to solve this problem of dimensional inequality. Because you have reduced it from here to the case of the shifted harmonic. So what does it mean? It means we already know what the eigenvalues. We don't need to solve it anymore. We have already done it. So what are the eigenvalues? So this is a quantum harmonic oscillator, and the allowed energy values is n plus half h cross. Compare it to what we got with the semi-classical approach. So if I go back, the semi-classical approach was actually not very far off. It was half into n h cross omega c. So the separation between energy levels was h cross omega c. So you got the separation right, but the exact formula is different. N plus half is something. The current values, the eigenvalues are h cross omega c n plus half. So it's still, you have certain allowed energy levels which are separated from each other by h cross. Is it clear? Great. Now, let's calculate how does the density of the states change. So when my magnetic field was 0, the density in 2 dimensions is constant. We know that. So up to my allowed energy level, which we call as the Fermi energy, my density of the states is constant, all the values of energy are. Now what happens when you apply a magnetic field? When you apply a magnetic field, it turns out that not all energy inputs are allowed. We see that only certain values of energy levels are allowed, and they are separated by h cross c. Which means my number of allowed energy levels is now reduced. At t is equal to 0, it will simply be straight lines, which are Dirac-Delta functions. But at finite t, and it will solve at finite t, this is actually very long. But still, that's why we need to go to lower temperatures, such that this thermal broadening is still much less than the energy gap, or what we call is as the h cross omega c, the gap between the magnetic field. Such that this gap is actually larger than the thermal broadening. That's why we need to go to lower. At t is equal to 0, my density of state is going to be short straight lines, but at finite there will be problems. We need to go to lower temperatures so that my gap, which is introduced with the magnetic field, is larger than the thermal. Okay? Now, if I have a material system, I have some carrier density. There are some number of electrons. Alright? Now I apply a magnetic field. These electrons occupy various states. Now electrons in state. Right? These electrons still has to occupy energy levels. But now the number of allowed energy levels is reduced drastically. Which means that each of these energy levels is tiny to each other. Is this clear? Yes, no? If I have certain fixed number of electrons and certain fixed number of energy levels which they occupy, now I am saying that number of energy levels which will be occupied, I reduce them drastically. Which means that whatever energy levels are there, the electrons have to fill only those. Which means that each of these energy levels will be highly integer. And we can calculate that integer basically. So these energy levels is what are known as lambda levels in terms of. So this was first shown that gauge is known as the. So you get the calculations. So we have energy levels which are kind of separated by exposures. Yeah. Each of these levels are. And we are going to try to find out what is the legitimacy. And then from there we will try to see if we can explain why it is. So till now we dealt with wave function. Okay? Sorry, till now we dealt only with the energy eigenvalues. Yes.
এখানে পুরো অ্যানালাইসিসের মধ্যে ইলেকট্রনের স্পিনকে নির্ণয় করা হয়েছে তো সেটাকে
For now, yes.
তো তাহলে নিউটনের আমরা টোটালের পুরো অ্যানালাইসিস কি এক থাকবে?
Yes, it will remain the same. Only thing is that let's say that the energy level is large, so they will also again split. Okay, I will show you one graph later. Okay, so how the magnitude restricts the energy levels, I will show you. But that term will just be added. This entire analysis and calculations and everything between the physical aspects of what we call of lambda levels that will remain. Okay? So till now we dealt with energy eigenvalues. But now we also know that wave function. We also, after solving this equation, we will also get the wave function. So what is the wave function for quantum number system? Okay. So now if I write down the full wave function, so we have plane waves in the y direction, e to the power I k y, and in the x direction I can write this one. Okay? And I can also, these wave functions as we can see cos of e to the power minus x square by 2 till v square, these wave functions will be localized in x direction and extended in y direction. Clear? So you can actually have based on the integer values, you can draw the wave function. N equals 1, n equals 3, n equals sorry, n 1, 2, 3, 4. For different values you can draw. Okay. Now let's try to find out. Let's say that if now we will try to find out the condition for the orthogonality of different wave functions. Okay, let's say if we have one orthogonal state psi n into k, one n comes from this, okay, and another quantization factor k comes from the eigenvalue because we allow values of momentum will be implied. So if you solve for the equation, so you get 2 pi by L momentum. So from there you get another factor over the k. It will be explained, it will be understood. So let's say if I have one particular orthogonal wave function which is psi into n into k, and the next orthogonal state is psi into n into q, then the condition for orthogonality is psi star into psi integrated equal to 0. Now if you know this, integral of psi star into psi integrated over space and that will become 0. Okay? Now, how are the allowed values of momentum separated? They are separated by 2 pi by L. Consider a problem of conservation. The allowed values of momentum are separated by 2 pi by L. Those who have solved Schrödinger's equation basis on this. Yes? No? Yes? Good. So that means if I have one coordinate xk, the next one is separated by xk plus 2 pi by L into x square. Why? Because xk is k by into x square. So different allowed values of momentum are separated by 2 pi by L. So x cube is equal to xk. So if I have this one orthogonal state at xk, the next orthogonal state x cube is equal to xk plus 2 pi by L into x square. Okay? Now if this is my x direction, you see in this figure, this is my x direction of the sample, and this is my y direction. Let's say I give some length to the sample along the y direction, which is L. So now what I want to calculate is a quantity which is known as flux between two neighboring orthogonal states. So what is the formula for the flux? Flux is magnetic field multiplied by the area. Okay? Magnetic field is V. Now to get the area, so if I have a rectangle over here, I need the length and width of the rectangle. Okay? So across one direction, I have already said that this is L. Okay, along the y direction. Why? Because we have plane waves along the y direction and the allowed values of momentum is related to phi by L. This is something we already discussed. So along this direction is L. And along this direction, we already calculated the orthogonality what happens. Xq is equal to xk plus 2 pi by L square. Which means this distance is 2 pi by L into V square. And along this direction, it is L. So now I multiply V into L, which is this, multiplied by xq minus xk, which is 2 pi by L square. Now, if you see L and L cancels out. Alright? And LB actually has magnetic field into and h bar by V, where h bar is h over 2 pi. 2 pi also cancels. So the flux between two neighboring states is h over E. So between two neighboring orthogonal states, we have one, and this value of flux h over E is known as one flux quantity. So neighboring orthogonal states have just one flux. Is this clear? Or if you have any questions? We have not done any fancy calculation to get this. We just use what we know from our basic quantum mechanics course. Allowed values of momentum separated by 2 pi by L. Then we want to find out when will the two neighboring, what is the distance between the two neighboring orthogonal wave functions. It is x cubed plus 2 pi by L into V square, because we assume that xk is equal to k by V, weighted xk equal to k by L square. And we just multiply V into area. So L cancels out. That's why it doesn't matter how big your sample is. So V L cancels out, turns out flux between the neighboring states is 1 volt. Okay? Now, in order to find out how many states are there, all we need to know is how many flux. Because if we know the number of flux quanta, we know the number of states. Okay? Is this clear? So this is how we can easily calculate what the generation is. And we also define something called as the flux quantum density, which is the total number of flux quanta in a unit area. This is equal to B multiplied by the area, which is 1, divided by I naught, which is 1 flux quantum. So this is the flux quantum density, and we define N as the total number density divided by the flux quantum. Alright? Now, once you do all these things, now I'm going to explain the quantization approaches. Alright? So Rxy is equal to B by N. This is something which we calculated in the first slide when we were discussing the classes of all pair. Now your N is equal to N by N phi is equal to mu, which is an integer, because the total number of flux quantum is an integer. So this is equal to EB by H. If you do this calculation, it means that Xy comes out to be 1 by mu. This is one hand-waving way of flow that your transverse resistance is actually quantized in radius of H products. Okay? But we can also understand it easily. As I said, we should be able to visualize it, not just calculate, we should be able to visualize in your mind. Okay. Now let's come to the same classical picture which I showed you. What you have here, you have electrons moving in circular orbits. Okay. Now in the bulk, as I said, only certain values of orbital, certain orbits are allowed. So these are some allowed orbits. So in the bulk of the material, the electron just keeps undergoing cyclical motion, which means that they do not contribute to my transport. Once the electron starts undergoing cyclical motion, it just keeps doing that. Remember, the electrons are of very good quality, so the material is very good quality. So there is not much scattering happening there to move the electrons from their orbit. So your electrons in the bulk of the sample are simply undergoing this cyclical motion. But what happens at the edge? At the edge, the electron is trying to undergo a cyclical orbit, but before it can continue the orbit, it hits the wall. And then it just keeps bouncing. So which means that the bulk of the material is actually an insulator, because the electrons in the bulk do not contribute to transport. But at the edge, the electron keeps hopping because this is a skipping orbit and moves along the edge. So now to make it what I said about this is that you have an insulating bulk but conduction along. So now something similar is coming up. Okay? So your electrons keep moving along the orbit, along the edge. So electrons keep moving along the edge. Bulk becomes insulated. So from semi-classical picture, what you see is that if you have a good quality material, you put in a particular magnetic field, a quantizing magnetic field, your bulk becomes insulated, and your electron actually moves along.
This is where I don't make it even one. Let's just stop you the reader.
It's just in this image. Now let's do the quantum picture. In the quantum picture, what do we see? Now you see this is see the axis very clearly. Here the axis is x and y. Alright? Here the axis this is energy and this is x. Which means that this is along the sample. Alright? So if I have a 2D system, this axis is along the sample. Okay? Now what happens? So along, as we said, we have certain allowed values of energy levels which are separated by h cross units. Okay? But what happens at the edge of the sample? The electrons cannot escape the sample. Right? Which means that at the edge, my potential has to be increased. So that electrons cannot escape the sample. But when I talk about edge, this is the physical edge of the sample. Okay? So when the electrons come near the edge, the potential has to increase so that it does not escape. Clear? Which means that in the bulk of the material, this is my energy level, then along the edge, it increases surface. Clear? So if I draw the energy level as a function of position, we have constant energy levels, but along the edge, it increases. Now, it depends on how many of these levels are. Let's suppose that the value of magnetic field and the density is such that this dashed line is my chemical potential. Or Fermi, let's say equals. So if my chemical potential is here, like this, so that only two levels are occupied. Okay? All the energy levels below the Fermi energy are occupied, all the energy levels above this are empty. So if my Fermi energy is here, what does it mean? If you see here, that means that only along the edge of the sample I have states which conduct along the two edges. In the bulk, there are no states to conduct. In transport, only electrons which have energies which are near the Fermi, only they continue to transport. Okay? You know, you have heard of this. So if you apply, let's say if you have a Fermi circle, you apply a tiny electric field, you shift it tiny. Only the electrons in that tiny shift, only those electrons actually contribute to transport. So if you see over here now, what happens if you have your Fermi once again, if you have your Fermi energy over here, then in the bulk of the material there are no states to conduct. But near the edge, depending on how many levels are filled, there are two levels which are filled, you have two edge states. If I bring the Fermi energy over here, there will be a single edge state. If I bring the Fermi energy up so that there are three levels which are filled, there will be three edge states. But the bulk is always insulated. Only the number of edge states that match. Alright? In this particular quantum Hall effect picture, when you apply high magnetic field to a thin material, then my bulk becomes insulated and transport happens freely along the edges. Okay? And the direction of motion of edges, now there is no spin involved here. Okay? As your colleague, your friend pointed out, we are not considering spin. It means that all the electrons are moving in one particular direction for now. And that direction is decided by the direction of the magnetic field which I have applied. If my magnetic field is in up direction and my electrons are moving clockwise, the moment I turn the magnetic field down, it will zone down. Okay, this is what is happening. So as of now, the direction of motion is determined only by the magnetic field which is applied. Alright, now there are two edge states, three edge states. Now there was an organism which was given by Landau. He actually showed that one edge state, a one-dimensional transport, we have one particular mode of transport, in the conductance which is added part is E squared per edge. If you have n modes, then the conductance is m into p square h. This is exactly what's happening over here. So as of now, there are two h states. So the conductance which you will measure is 2p square. In terms of resistance, it will be h over p square. Alright. So with this also you can explain the polarization without doing this. Yeah. Okay, clear? So the quantum Hall effect, what happens in quantum Hall effect, even though you have a barrier which is 2p, your transport is actually only along. Right. So this is the picture, right? So now we started with Hall state, and now you have understood, at least got an idea, you understood what is a quantum state. You apply what is a quantum Hall state, you apply the perpendicular magnetic field, and you showed by solving for this equation how your lambda levels are formed, and depending upon the number of lambda levels which you occupy, that determines your data distribution. So now let's say you have applied a perpendicular magnetic field. Let's suppose the magnetic field is in up direction, positive z direction, and you have up spin electrons which are moving in counterclockwise. Let's suppose this is moving in counterclockwise. Now this is a state with broken dynamic resistance. So the magnetic field actually breaks the dynamic resistance. Now we will ask the question: what happens under time reversal? Now, under time reversal, the time reversal state has opposite momentum and opposite spin. So, if you have a state, let's say, where your upper spin electrons moving in counterclockwise direction, under time reversal, the spin will become down and the movement will actually, the time reversal state has both opposite momentum and opposite spin, which means that the direction of motion will be constant. It is as if the effective magnetic field is reduced. Clear? Effective magnetic field is reduced. Now, what do I do? I bring these two quantum Hall states for opposite. So now my effective magnetic field is 0, but what I have is one up spin electron moving in counterclockwise direction and a down spin electron moving in clockwise. Effective magnetic field is 0. Now you have my up spin electron moving in counterclockwise direction, my down spin electron. So we get counterpropagating. And this state is known as the quantum state. Now, what is the difference? As I said, this is a two-dimensional topological display. But when I talk about the quantum Hall state, the quantum Hall state is also a topological state. In fact, it was discovered in 1980s, and within a couple of years back then itself, people already knew that this precise quantization of resistance in the quantum Hall effect is actually due to topological order. So the fact that the quantum Hall state is a topological state was known in that. Right? Because it's protected by that, it's protected against. Okay. Now, I have been saying something that is protected against the scattering. And let me try to explain what happens. Why do we say that these states are protected against the scattering? Let's say this is just my 2D system. And this is my edge. Electron on this edge moves in this direction. Electron on the opposite edge moves out. Okay? The bulk is insulated. What does backscattering mean? Which gives rise to resistance. What does backscattering mean? Backscattering means, let's say, if I have an electron moving in this direction, it encounters an impurity and it backscatters. Which means that instead of going forward, it just scatters by 90 degree or whether it's large and it starts moving back. That's what increases the resistance. Okay? But now here, the direction of motion is imposed by the magnetic field. An electron on this edge cannot move back. It has to always move in this direction because of the magnetic field. The electron will always be moving only in this direction. Why? Because there is a dialectic associated with that. Because of that. The only way for electron to backscatter is that it has to come to this edge. Because in this edge, it is allowed to move in this direction. which means the electron on the upper edge will be this direction. If it wants to backscatter and come back in the reverse direction, it has to come from here. Of course, you can say, okay, so what? It can come from here to here, scatter. Turns out that the samples which we make, this can be really large, even millimeter. On 1 millimeter turns out to be 9 it is very small, but for electron it's still large. For an electron to jump from one end of the sample to other edge across a millimeter, sometimes it can be even larger, 2 millimeters. Something catastrophic has to happen. Okay? So that is why the edge generals of the quantum Hall effect also are protected against impacts. So now, as I said, I showed you how you can quantum Hall state. This was quantum Hall state is also a topological state, but in order to form that, you need to break the time universal symmetry. You need a time universal. Quantum spin Hall state occurs at these and under time universal symmetry, so that means the time universal symmetry is not closed. Under time universal symmetry, these states are protected against transference. So this is a quantum state. Of course. Now, of course, in lab, that is not how we construct. We don't take two opposite. This is what just to explain it conceptually, so that you can visualize. In lab, we actually don't do this. We don't form one quantum Hall state, then we form another quantum Hall state, and then bring them together as one. So now I will show you how we form this. Alright? So the prediction actually to see the quantum Hall effect, it came in 2005 from these two physicists from University of Pennsylvania. So this is known as Kane and Melimon, and they predicted that quantum spin Hall effect can be observed in an alien system called as neutron. Or we have heard of two-dimensional system, two-dimensional carbon. So they predicted that there should be a system. But the band gap, bulk band gap, systems are gapped in the bulk and conducting states at the surface. That band gap, bulk band gap is very tight, 10 microelectrons. That is very, very tight. So definitely 25 million. This is 10 microelectrons. Which means you need to go down to really, very good temperature. So it was not very easy to observe quantum spin Hall effect in this particular. I'm talking about 2005. It doesn't mean that it is like not usable. Okay, this was 2005. Some people have actually, what they have done is that they have taken graphite, they have approximatized the highest non-propagating so that you increase the gap and try to observe this non-propagating. But just a year later, this was in 2005, about 1 year later in 2006, three physicists, Raychaudhuri, Taylor, which is the exact. They are effectively there. They actually showed that instead of graphene, it's much better to use a hollow cell right. Well, was there by changing the thickness of the quantum value. You can induce a phase transition above a certain value of thickness. You can observe a quantum spectrum. So you can have a plausible phase transition as a function of thickness, where you transition from a normal insulator or a trivial insulator to a logical insulator. And the Hamiltonian is in short is known as a plateau. Alright, so how did I do it? When I say that you have a topological phase transition, and that means predicting something called a band inversion. Okay? Now, when I say band inversion, it automatically applies that whatever B is inverted, there is some sort of inversion happening as opposed to the conventional difference. So let's say a normal band structure, in order to simplify the terminal of let's consider S-line formation of helical. So normal, this is the normal ordering of S-line. Yeah, S-line particles. For this is a normal band structure. For an inverted band structure, this ordering will be reversed. And this inversion can happen due to relativistic. Okay? Now, we will not go into detailed calculation, but some materials can have an inverted band structure in which the S-like bands will actually be lower in terms of the. Now, in both these cases, the bulk is gapped. Just the ordering of these bands have been. This is a schematic. What about the normal material? So, what we are talking about is multi-metal, right? All the topological properties of multi-metal, right, actually happen. So, we compare two materials. One is cadmium telluride, and another is multi-metal. Both of them are actually zinc like this conductors. They are very similar structure. Only difference is that multi atoms. So when you actually consider all the connected terms to find out how the energy is exchanged, the most dominant term is what is known as the mass velocity. Now the mass of mercury atoms is much more, which means that this mass velocity term, and if you see for cadmium telluride, it reduces the value of gamma s or gamma 1. So it reduces the value of gamma 1 from there to here. So the change is not much, but for mercury telluride, it still remains higher than this. But then what happens? Apart from mass velocity correction, we have a spin orbit. Now the spin orbit term doesn't affect the s. Okay? The spin orbit. The spin orbit term doesn't affect s, it affects the p. So the p1 is splits. If one of them is split into higher energy, one of them is split into lower energy. So once it is split, you see one p-type band, it actually goes above. So this band. So due to these connection terms, the ordering of S can be reversed in multi-term. And this is something which was, once again, this is also not used for so many backscattering. So even in 1972, people knew that multi-term actually has an overlap. But yeah, it takes a while for actual utilization of that to reflect in experiments. So now if you see over here, so we consider at the runoff, we consider the band structure only at the runoff wing. So if you have done the condensed matter course, you will realize how many band structures along different symmetry. Okay, so this is P versus K, but along different symmetries. So you have difference. What we consider is at the gamma point. So if I zoom in there, what we see is there are two types of band. One of them is gamma 6, and then we have the W degenerate gamma 8 bands. For normal cadmium telluride structure, gamma 6 will be higher, and W degenerate gamma 8 will be lower. Okay. So now if you take an intrinsic crystal and you start filling up, then your Fermi energy will actually lie at the intersection point of this W degenerate gamma 8 bands. So now, at best, this is actually still a semi-metal or a topological metal. In order to convert it into a topological insulator, you just need to open up a gap. And how do you open up a gap? We form valence. We actually confine these. That's why we said that quantum valence. When you confine this material into two dimensions, if you reduce the thickness, then another energy comes into play, and that is known as quantum confinement. And that actually breaks the criteria. Okay. Now, of course, there have to be in a certain sweet spot because otherwise it will re-invert the order to become a trivial order, to become a trivial maximum. But we won't go into. And then what do we do? We actually make an interface of a normal insulator. Now I have coded it in terms of color. Let's say this red inverter is the valence band, and this is the conduction band. This band capital is denoted with color. So if you see for inverted band structure, yeah, this is a normal insulator. For an inverted band structure, the blue is higher than red. But the moment you make an interface between them, you can do it either with band or you take a material with a normal insulator. So if you have mercury telluride, you put cadmium telluride on top. You have one normal material and one you have an inverted structure. You make an interface of this. At the edge, what will happen is that this blue band sees that my character band, my current band is over here. So you can try to blend up in the red and then so for a normal, when you make an interface of a logical insulator with a normal metal or with vacuum, and at the edges the band gap exists. So in the bulb you have an inverted, in the bulb you have a gap, and at the edges alright. So if you see if I zoom in, so here there are two states. This is my Fermi energy. So on one wall state there are two states. And the direction of propagation of these two states, if you take the slope of this, you see that they are opposite. Which means that these two states are convertible. Alright? So if I cut it, it's the same thing. I get it. Now, how to measure it? How to measure that there are two states? Very simple. Simply measure. You actually take a normal material where the band is normal, not inverted, and you take an inverted material. And you tune your chemical potential from conduction band through the band gap to the valence band. And if it is a normal material, then when you are in the band gap, my conductance, measured conductance is slow. But for a topological insulator, when you are in the gap, your conductance will be becoming only one edge state, and there are two edge states, the conductance will be squared. So, in order to measure it very simply, apply a voltage to measure the current, calculate what the conductance is, which will stop. For a normal material, when you are in conduction band, you have a finite conductance. When you are in valence band, you have finite conductance. Here you have conduction with electrons, here you have holes. So, when you actually move the chemical potential to the band gap, your conductance will become zero. But for a two-dimensional topological insulator, you have two edge channels in the gap, so you will measure the conductance. Alright, and this is exactly what was done in 2007 in the science paper. They actually measured one of the two thicknesses, and this is the thickness for which you expect the quantum spin object, and there they show that they have done this. This was the first observation. Okay. Any questions?
Quantum element. That the resistance inverse, I would say, is equal to h by h squared j, where j or mu whatever
Yes.
number.
Yes.
So that doesn't explain how experiment could be gained between those two values straight or constant values. We're seeing peaks and plateaus in resistance, but how does it get better?
Okay. So your question is that why for a full range of magnetic field the resistance is constant? Is that your question?
Sir, in formula, you're saying that there are certain values for which we are getting certain resistance.
Yes.
That's understood. But between those two values, we get a constant value.
Okay. Very good question. I am going to change the presentation a bit because I want to explain this nicely. It's a very good question. Okay. Let me check it. I have a mistake with the alpha. So ideally what should happen is that for specific values of magnetic field, you should see just pointing. But what we see that as the magnetic field changes, my resistance remains constant. Let me see if I have a slide. So when I said that the material has to be really, really thin, I hope I have it. Yeah, do that. Okay. So these are my. So here what I'm drawing is the potential. So this is the x direction of the sample. So in the bulk, I have constant energy, higher energy levels. The separation between these energy levels is h cross by omega c. Okay, so h cross by omega c. But along the edge of the sample, as I explained, the potential. All right. Now, bulk states do not carry any currents. There are no states along the bulk. So what happens when you actually move the chemical potential? What should happen here? So what should happen here is, as soon as, let's say, you are coming from here to here, I'm increasing the magnetic field, which means that from 3, it actually comes down to 2. Then I increase the magnetic field to 3. The moment the last electron from this level becomes empty, my chemical potential should just jump here. Because there are no states in between these two lambda levels where you can pin the field. So ideally, I should not have a long range of magnetic field for which my value of Rx is constant. So why do we see these flares? Turns out that if you have a perfectly clean sample, you will not see. But in practice, these levels in between them, there are some mistakes, which we call as the mid-gaps. The sample is not perfectly clean. There are some impurities states. When your chemical potential is here, as your last electron moves out, your chemical potential actually goes through all of these states. Even though you don't have any conduction from them, your chemical potential increases as you keep changing the magnetic field. Your chemical potential doesn't jump up. It goes through these values. It means your chemical potential actually goes through the gap. And for the value of magnetic field for which it actually goes through this gap, your Rx is so you need some tiny amount of disorder to make the plateaus exist. Okay, I'm not saying that disorder causes quantum Hall effect. Okay, very clear. Quantum Hall effect happens because of the resonance. Random levels of in order for plateaus to be visible, you need some amount of resistor, some mid-gap states between so that your chemical potential can actually go through this. Okay? So this is why we observe the plateaus. Otherwise, for perfectly clear sample, you are absolutely correct. We will not see the plateaus. Very good.
To be the manufacturing industry, so you need to generate the studies how is it industry.
Yes.
Yeah. We have the robotics, then no longer so physics after examples of and that we see. So you have the robotics states in one time, and in the surface you have the steam.
Interesting. The problem for the quantum spin orbital, the moment you hit the ferromagnet, it will break time resistance. And the moment the ferromagnet breaks time resistance, when the topological edge is there no Yes. The states of the otherwise there is no topological protection. You apply ferromagnet, it will break. Okay, so this is how this is seen by the group in and this was actually done in this book. Professor the same place where I did my postdoc research in the same field. So I don't know if this is exactly I joined much later than this. Now it's not very straightforward. The material actually is thrown in the lab. So mercury telluride is thrown in the lab as a technique called as a molecular beam tax. So all that we study those physics are actually doing things which we have to do things with hand. Grow the material to make the setup. So this is actually an EEG room where there are many, so if there are many connected chambers and this, the management of this needs of challenges. There are people who are dedicated just to handling systems. And very high the molecular taxing is a method by which you can go to the highest areas. The pressure inside the temperature chamber will be almost 10 to the power minus 11. Atmospheric pressure is around 1000. So it will be 10 to the power minus 11 really large, you see different kinds of pumping systems. Rotary pump, black water, molecular pump, or ion pump. So you achieve very, very high vacuum so that you don't have that. Still, you cannot have a perfect vacuum. It's 10 to the power minus 11 too fast. So some defects is still managed to pass. And then after that, so this is a zoom picture of it. And we don't actually, you need to, when you confine them, you see in this is the band gap and this is the lattice constant. So if you see here, substrate which we use for scattering the right, then lattice constant is actually very close to it. So now if you try to grow two materials of very different lattice constants, they straight so you have to take care of it, you have to take into account lots of things. So people don't just actually grow on cadmium telluride, they actually sandwich mercury telluride within cadmium mercury telluride. The advantage of using cadmium mercury telluride is by changing the mercury ratio or mercury content, you can change the lattice constant of that. So you can apply the fixed amount of this range you want. Okay, I guess I should stop. Right? I have something else, but I will stop. So then I at least introduce some concepts.
Time for questions, please ask.
I just have one question that in an earlier slide you talked about flux quantization in the negative state. So the value of flux was H over E. So from সুপারকন্ডাক্টরের ক্ষেত্রেও আমরা যখন কোনো একটা হেলিয়ামের ফ্লাক্স কোয়ান্টাইজেশন সেটাও h বাই a এবং দুটোর ভ্যালু হচ্ছে একই দুটোর মধ্যে কি মানে সেটার কোনো কানেকশন আছে?
Okay, so both of them are very different phenomena. A confusion to origin because I also showed there that your longitudinal resistance goes to zero. So people might think that okay, here also resistance goes to zero. We have one flux quantum, but in this case, in the quantum Hall state, there is no superconductor. Your Rxx goes to zero, exact zero, but that does not mean the total resistance of the samples. It is zero, only Rxx is zero. That the fact that it appears to zero has to do more to do with the measurement geometry. But the resistance of the sample, so this measurement geometry which I indicated here, this dog is something which is very good to clear.
Amal.
Alright, so this was my direct, and let's say this is my academic field. So I mentioned from here, Rx. Only for this particular measurement geometry, you have X-axis. Instead of measuring it, this is my I plus, this is my I minus, this one. If I number the facts, 4, 5, 6. So my I is 1, 2. And measuring equal to 2. And then I see that my opposite terms are these two. So R equals 4, 1 equal to V34 divided by R square. This turned out to be 0 because I measured a 0. Alright. If I measure just this, if I measure R 1 and 0, I is 1 and 4. E is 2 to 3 or 5 and 6. So this will be R should be 3, 1 and 4. Okay. So this is 2. So if I measure R 1, 4, 1, 4, I will still get just H over in the calculation. And the way for doing the calculations like this, there is a formula is known as Landau-Rudiger. Okay, Landau-Rudiger formula. It tells you how to calculate when you have edge currents, how to calculate the value of resistance which you will measure for different visual formations. So if I change the geometry, I will measure. Okay, so Rx is equal to 0 is 1.
আমি আছি Rx এর নামে আছে সুপার কন্ডাক্টর এবং ইন্টারনাল ওর ক্ষেত্রে যে ফ্লাক্স কোয়ান্টা সেটা দুটোর এক্সপ্রেশন আমরা এক্স্যাক্টলি রাখি তো সেই জিনিসটা তো স্ট্যাটিস্টিক
Yes.
আর আরেকটা জিনিস সেটা হচ্ছে যে আমরা এখানে ম্যাগনেটিক ফিল্ড অ্যাপ্লাই করা হলে আমার জাস্ট মানে আলফা ইনসুলেটিং ক্ষেত্রে রয়েছে তো এই জিনিসটাকে যে কোনো ম্যাগনেটিক ফিল্ডের জন্যই মানে অ্যাপ্লিকেবল মানে আমি ম্যাগনেটিক ফিল্ড যদি আর্টিফিশিয়ালি বেশি পড়ে তাহলে মানে ফেসটা ভেঙে যেতে পারে
Okay. So at what magnetic field you will have these platelets, that depends on various factors. What is the density of your material, how clean your material is, it depends on all these factors. Okay. So if you take two different materials with different densities, then your things will change. For one particular material, you will need to apply a different magnetic field in order to reach the same friend. Okay. Now, arbitrarily high magnetic field you apply, there is some experimental limitation also. People have measured these things up to 70 Tesla. As I said, for high magnetic field, even at moderate magnetic field, whenever we see the quantum Hall there. So you will have, like I said, you will, like I said, we will also see fractional Now, there are various kind of fractions which are allowed 5 by 2, 2 by 5, different odd fractions, 1 by m type, so 1 by 3, 1 by 5. There are a lot of fractions which are allowed, which I have not discussed. That is called fraction. Okay. So, a very high magnitude it goes vectors. More questions?
Any other questions? No, then let us thank the speaker from
One thing I wanted to mention on 25th Friday, there will be a program at Presidency to celebrate April, actually technically April 14th is the Quantum Day. Whole of April month is World Quantum Day. So there will be a program at Presidency Center from 11 to 1 on Friday, 25th. So students are very helpful. Depending on my class,
like visitors.
but I think you also get an informed that it's international. And also, if you want to visit the center and visit the lab to see the facilities which we have, research facilities, you have to do. We have a summer internship program for this, and